discuss a little bit more about inverse functions. We're going to get into how to find them. We're also going to know more about their derivatives before this day's notes is over. So, let's get started. I'm going to begin with a couple example problems that will open your eyes to some thoughts. So, it says if f of x equals x plus cosine of x, find f inverse of 1. So, what that means, that in the inverse, that's going to be the point 1 and some unknown that we are expected to find. Which means in our original, because the domain and range switch, that's going to be some unknown with a 1 for a y. So, how can I find that unknown? I have two options. I could find the inverse and then plug in 1, or 1 for x, or I could plug 1 in the original for y. Option 2 sounds better to me. 1 equals x plus cosine of x. What angle plus its cosine value equals 1? Well, x is 0. Think about that a little bit. Graph it if you have to, whatever it takes for you to find that answer. But if you think unit circle, you should be able to find it. What's the domain of the inverse function for f of x equals radical 3x plus 7? Well, the domain of the inverse is the same thing as the range of the original. If you think about this function, radical 3 plus 7x, its base function or parent function or mother function, whatever phrase you like to use, is radical x. Radical x looks roughly like that. Now, think transformations for a second. What do the 3 and 7 do? Well, the 7 compresses it horizontally, and the 3 moves it left 3. So if I compress this horizontally and move it left 3, what happens to my lowest y value? Doesn't change. So our range of f of x is going to be 0 to infinity, which is also the domain of our inverse. So this 0 to infinity is what we need. The range of this function, therefore the domain of the inverse. Example 3 says if function f of x equals 3x plus 4 has domain from 2 to infinity, what's the range of the inverse? Well, let's talk about that. Domain 2 to infinity, that's the original. We think about this, we need the range of the inverse. That's the same as the domain of the original. Well, they give us the domain of the original, so automatically that is also the range of the inverse. If the function f of x equals 3x plus 4 has a domain from 2 to infinity, what's the domain of the inverse? Well, we want the domain of the inverse. To get that, it's the same thing as the range of our original. So, I know that my domain is from 2 to infinity. So, if we think about this graph for a second, 3x plus 4 looks roughly like this, but our domain is from 2 to infinity, so we're only talking about the portion from here this way, at 2. How can we figure out what that y value is? Now, lowest y value that occurs when x is 2. Well, we can plug 2 into our function. And we find out that it's 10. Notice that point right here is the lowest that that portion of the graph ever gets, and it's just going to continue to get higher because it has the slope of green. So, our range is going to start at 10 and keep going up. So 10 to infinity. Now, let's talk about finding inverse functions. Right? Y equals f of x. Solve this expression for x in terms of y. To express f negative 1 as a function of x, interchange the x and the y, and the result will be the inverse. They might have worded it a little more as need be. You've done this before. We know our function is y equals 2x plus 5. I think the easiest way is to switch your x and your y and solve for y. So x minus 5 equals 2y. Y ends up equaling x minus 5 over 2. Rewrite that. X minus 5 over 2. So, instead of y, make sure you label your work f inverse x minus 5 over 2. Let's try. Okay, let's try another one. Same idea. This one's a little bit trickier. We know y is x minus 1 over x plus 1. If I switch my x's and my y's, just pick one x to switch. You got to make all of your x's into y's and all of your y's into x's. Now I'm going to solve this for y. I'm going to begin by multiplying both sides by y plus 1. On the left, I'm going to get xy plus x. On the right, I'm going to get y minus 1 because my y plus 1s will cancel out. Now I'm trying to solve this for y. Part of my problem is that I have a y on both sides of my equation. So to be able to solve it for y, I should probably get those on the same side and things that are not y don't have y's on the other side. So xy minus y is going to equal negative 1 minus x. I move my x over there and move my y over here by subtraction in both cases. Now, how do I get 1y if I have more than 1? Well, I can pull it out. If I pull it out, I'm left with an x minus 1. And on the right, I still have my negative 1 minus x. How do I get y by itself now? Divide by x minus 1, and then y equals negative 1 minus x over x minus 1. We don't believe y because this is the inverse. You might also end up with, if you move things to different sides, 1 plus x over 1 minus x. That's what happens if I take a negative out of the top and get it to the bottom. So 1 plus x and 1 minus x could also be the inverse. Now finally, we have a rule. The reason we have this rule is because sometimes we are unable to find the inverse. A function just has too many y's, or has a y cubed and a y, and nothing will work for us, not even the quadratic formula. So we're going to pretend for a second that f and g are inverse functions, and suppose that f of a equals b. If f prime of a exists, and f prime of a is not equal to 0, then g prime of b also exists, and if I want the derivative of the inverse at b, that's equal to 1 over the inverse of the original at a. How do we get the original at a? Well, we plug b into our inverse. So this is going to make a little more sense when you see an example here in a moment. So I want to find the derivative of the inverse at 1. So I want to find f to the negative 1. One second, put that in parentheses, at 1. To do that, I have to do 1 over the original prime of the inverse of 1. And it might come down to just you memorizing this formula, maybe not really wrapping your head entirely around it because it's kind of a difficult concept. But let's talk for a second. So I know on my inverse that I have, right here, on my inverse, I have the point 1 something. And I know that on my original, that would make it the point something 1. And first thing I need to do is find f is inside parentheses in our denominator, the value of the inverse at 1. Well, to find this number, I can plug 1 into the x value of the inverse, which we haven't found yet, and would not be very easily to solve for that x into x plus cosine of x once we've turned it into a y. So I instead am going to use this idea that on the original it would have a y value of 1. So I'm going to plug 1 into 2x plus cosine x. And if I think about this and look at my unit circle, 2 times an angle plus the cosine of the angle has to equal 1. We're going to find out that x is 0. 2 times 0 is 0. Cosine of 0 is 1. So 0 plus 1 equals 1. So now I know that, go back to the blue, we need 1 over f prime of 0, because this is 0, which means this is 0. The x value of our original function is 0, and the y value of its inverse is 0. So, now, I need f prime of 0. Well, let's find f prime. Our function was 2x plus cosine of x, so f prime is 2 minus sine of x. I need f prime of 0, so I'm going to plug into 0. And I'm going to find out sine of 0 is 0, so this is equal to 2. F prime of 0 equals 2, which means our f inverse prime of 1 is going to be equal to, keep the 1 in the numerator, f prime of 0 is 2, so our answer to this problem is 1/2. Study this a little bit, rewind and listen to part of it again if you need to. We can talk about it some more in class tomorrow. Questions?